Hey everybody, I'm Kenny. I work here in Vancouver at the Embassy VFX. And today I'm going to talk with you guys just a little bit about our delayed load rendering workflow and how our assets stay nice and packed in an alembics straight through to rendering. The goal for us was to make nice light assets that the lighters and look dev artists can work with nice and easily. So here's an example of, we worked on Lost in Space, the Resolute, the giant mothership. And this is just a turntable. Oops. That was supposed to loop. So just to get an idea of the complexity of what we're capable of working with, hundreds of spaceships on the inside, lots of instanced pieces coming from Maya, and we'll get into how all that works after this. So let me start the presentation here. All right. So first I'll go over our asset structure. There's basically 5 main areas inside of each asset. One is where the artist does the look dev. Then there's the shot level look dev area where you can make changes, shot-based changes and overrides and all that stuff while maintaining deferred load geometry. Then there's the mesh shapes, which is basically an area that, well, I'll go over this here. Sorry. So the look dev areas, the main asset look dev is done. I'm going to go over the types of incoming data, the use of transformation point cloud that is coming, being generated from the alembic from Maya, loading of data from the model and rig, methods of working with the asset data. We then bind the attributes from the point cloud onto each geometry piece that's instanced around. We write the look dev attributes and changes to a new alembic archive, and then publish the asset to an OTL for use within the shots. The shot level look dev area is where the data is optimized per shot and the shot level overrides and alterations take place. We load the cached look dev alembic archive, prepare the transform point cloud for shot specific elements, in the case that we're using multiples of a single asset. We prepare the asset geometry for shot-specific elements, how we handle shot-specific overrides and changes to assets, and then putting the geometry back into local space because we work on it in world space, and the goal is to use transforms as much as possible, not deformation. The mesh shapes area is where each unique mesh shape from the asset lives. And then the render area is where we reconstruct a collapsed rig hierarchy to utilize transform data for non-deforming geo. And also the deforming geo is in there. Then the shaders area is where all the materials are. And they're pre-compiled upon publish, so that way when we export all of the shaders, it doesn't take a long time for it to compile. The advantages of the workflow are faster and smaller IFD files. We have less batch license usage on the IFD generation side, and the machines can spend more time rendering rather than creating a render archive. Multiples of one asset type are instance of one master asset. So as I was saying, if we have 2 spaceship assets, they're all instances of the same geometry. Lighter and more manageable scenes for the lighting artist. The most common types of changes during look dev do not break the delayed load of geometry. Faster IPR startup times with compiled shaders during lighting, so the artists can look at a render quicker. So look development. First we start with the incoming data. We have an alembic file of the static asset model that comes from Maya. It's exported from Maya with the vertex rest position data in world space. That avoids us having to unpack the geometry and add the rest positions. which further helps with the delay loading of all the geometry. Data for which mesh is associated with which transform, so they all get placed in the right space. And we have auto exports of any attributes within our naming convention, so we just have a prefix that my artist can add on there, and we get all that data as it comes in. We then have a separate alembic file of the animation data. This contains only the transforms for non-deforming geo. The deforming geo is exported with the vertex rest position data also. And one of the only real requirements coming from Maya is that each mesh shape must have unique names regardless of where they're placed in the hierarchy. Unless, of course, it's an instance, in which case the shape name has the same name. So we then generate a transform point cloud. We use this to instance the static geo for rendering purposes. It contains various attributes used to transform mesh shapes properly for rendering. And basically, all of our transforms get brought into a collapsed version of the rig. So we use a convention that we call TRS at the embassy. And that's used to describe just a transform that's actually being transformed by the rig. So we're kind of ignoring all the groups in between, and we don't want to rebuild that entire hierarchy. So then we get from our proprietary Alembic tools, we get a list of attributes on each of those things, and we have the ABC full path, which is the full hierarchy path of the transform, the name of the mesh shape that's associated with that point, the resolve path, which is the full hierarchy path to unique mesh shape for instances, the transform, which is the combined transform matrix of the mesh from the lowest level TRS that it's under to the mesh's local transform. And then the TRS matrix we have, in case we need to use that at some point. And then the TRS path, which knows what TRS it's actually supposed to go under. We then load the Alembic in. The Alembic SOP is default delayed load. It's a packed Alembic type in Houdini. So as long as we don't unpack it, it will automatically get written to the IFD. The geometry won't be written in the IFD. It'll load directly from disk. Look dev work is done on geometry in world space. This allows us to see the model as we would in the end after transformations from the animated Alembic export are loaded. And then the world space transform matrix, we copy that also from the packed Alembic type, because when you unpack it, if you do have to do some geometry work, once you pack it again and it becomes just a Houdini packed prim, you lose that information. So we're basically storing that so that we can keep it. Methods of applying the look dev changes. Most of the time we work at the packed level, since each geometry piece is usually getting the same material. It depends. We just assign the materials directly to the packed prims. This is the fastest method. Just the shot material path, and you could set any other attributes that you may need for randomization or anything like that on these packed things. We can also work in the unpacked level. If the geometry requires the changes at the polygonal level, we can do that. We have a custom node that unpacks it, and then you can do your work, and it'll repack it again based on the names and keep all the attributes that you require. After repacking, we add an attribute on the packed geometry representing whether the shot material path attribute was added on the unpacked geo. So that way we now know if we have to swap shot material paths at some point, that geo says, okay, I need to be unpacked again and changed. Since our assets are built around being instanced, we do highly encourage the use of instancing coming from modeling. We use a custom instance data attribute to maintain instances in Alembic without actually writing all of the geo to the Alembic when the model is published out of Maya. This allows the light and efficient transferring of data from one package to another. Attributes on the transform point cloud are used to vary the instances. So the attribute data is bound to the point instance geometry using a Python-generated material style sheet. That we set that as a detail attribute on the point cloud, so that way it knows what attributes need to be bound to the geometry. And this allows us to do material overrides just directly on these points. We have a custom VOP node for using the attributes from the geo, the packed geo or from the point cloud in the shader. It checks for binding in that order, basically. So it's always going to look at the geo first, and then it sees if there's a packed override, and then from the point cloud it'll use it. And this is just a sample style sheet for the attribute binding. I don't want to get into too much detail with it, but it's pretty simple. It just basically takes each of those attributes that are on there and binds it to the geometry that's being instanced onto that point. We then cache out the lookdev geometry back to alembic again. The packed level data is copied to the transform point cloud for storage in a new alembic archive. This is because currently Houdini's alembic ROP doesn't support the exporting of packed level attributes back to an alembic file. The new alembic archive contains geo with the custom lookdev attributes and transform point cloud. Any geo that has been unpacked will load in again as packed alembic primitives, thus being delayed load. We also have an option to use BGeo instead of alembic in case non-mesh based primitives need to be included, such as cloud volumes or anything that alembic doesn't contain. The asset's then ready to be loaded into the shots and have its animation applied. So now once we're in the shots, we're able to manipulate that data further if we need to. The transform point cloud is extracted from the archive and unpacked. We copy the packed level attributes back to the geometry. And none of this breaks the delayed load aspect of it. It's just writing out those attributes to the IFD. This is all done using a series of Python scripts that know what attributes need to go onto what geo and whether it was a point, a vertex, primitive detail attribute. We also implemented a switch at the top level for debugging purposes. This just switches back to the completely unaltered shaded model, so that way we can debug between if our shaders are working or not, or if we're doing something weird to the geo. We then prepare the transform point cloud for the shot. The transform point cloud is prepared for the shot. The instance path is set dynamically and is based upon a set of rules. Is the asset set to load all from one asset? As I was mentioning, all of our assets, if it's multiple elements of the same type of asset, they're all going to instance from one master asset. The master asset is actually just chosen by a sorted list of the same assets. So assets can be explicitly set not to do so. Are there any shot level lookdev changes applied? If there are, the asset will automatically instance from its own contained objects instead of from the master one. And it's also no longer eligible to be the master asset. Are there other assets of the same version? If there's different versions of the asset mixed in the shot, that's okay. They're all just going to look for the same version that they are. Prepare the asset geometry for the shot. Although this rarely happens, shot material paths are automatically changed to match the namespace of the chosen master asset. Usually when we work with something, it's named after the asset that it is. So if there's a namespace, a 1 or 2 or whatever, we may have to change those paths because there's not the original one in there. They're changed in basically exactly the same manner that the instance path is set on the transform point cloud. The asset geometry knows that they are to be unpacked for the shot material path string to be replaced based on an attribute that we set on the packed primitive. Our tool that unpacks the geometry for editing creates this attribute in the shot material path attribute exists when it is being repacked. This helps to minimize the amount of delayed loading alembics that get broken due to having to alter their material paths. We plan in the future to make use of a style sheet to accomplish this instead of actually unpacking the geometry again. Shot level changes and overrides. There's an export and import section that we make use of instead of using an editable area in the HDA. We find that this is more beneficial for our workflow because it's contained within a separate subnet and it's publishable at that point. We can write it to an OTL and share it between shots or anything like that. It keeps our asset version tracking linked to the unaltered version of the asset. As I just mentioned, it makes publishing that much easier, those shot level changes. And any kind of materials that you change, since they are precompiled and saved in the OTL of the asset, you can just drop them down from a drop-down menu, drop down that material, change it, reassign it. We then move the geometry back to local space. Basically because we're using those TRSs to move the geometry around and using transformation instead of deformation blur. Sometimes the pieces are in some wonky places, which then gets fixed when it gets put under its TRS, but we prefer to work on it that way. The third area is the mesh shapes. This is just a subnet that contains a whole bunch of all the pieces of geo that are related to that asset. These are what gets instanced onto that transform point cloud. This is also where all of our render properties are set on those pieces of geometry, so you can set the subdivs, the ray visibility, all that. And that's all in local space. We then have the render hierarchy. This is the final step. This is what we render in the end. It makes use of the alembic XForm object and geometry objects to transform and instance all the pieces into place and make as much use as possible of a transformation blur. So as you can see on the hierarchy on the left, there's on the right there's all the separate TRSs that are related to the rig. There's a point cloud in each of those. So those are actually instance objects. They just have the instance properties on there. And then branching off to the right side, we can have deforming geo, and all of that gets loaded in there. The alembic X-forms are parent to each other. They represent the collapsed version of the rig hierarchy. We only consider transform nodes that are actually transformed by the rig, and these are identified by convention, what we call TRS nodes. This makes it so our non-deforming geo does not require deformation blur. Perfect. Non-deforming geo. They each have their own individual geometry object in the render hierarchy. Excuse me, I'm sorry. The geometry object has fast point instancing, as I was mentioning. It merges the transformation point cloud into the object. It then removes the points that are not associated with that TRS. The fast point instancing with the detail attribute style sheet binds all the parameters to those pieces of geometry as material parameters. Separate out the branch using a for each loop copy. Okay. We have a separate output branch so that dynamics and stuff can merge that geometry into whatever they're working in, and that uses a for each loop that will instance those objects as on a copy node, so that way they can merge it out of the asset, and it's not just point instances. The deforming geo, each geometry gets its own mesh shape. We try to keep our scenes as light as possible. So if the geometry from the mesh shapes has never been unpacked and altered in any way during the look dev stage, we basically just load in what was exported from animation. and then it remains delayed load all the way through. Yeah, it allows it all to remain delay load. If the geometry has been unpacked, we then have to unpack both the lookdev geo and the animated geo, and we apply the point deformation from the animated geo onto the lookdev piece of geo. This is the case if we have to change normals or anything like that, it maintains all the changes that we made. But we do lose the delayed load aspect of it at that point. And then the shader hierarchy. When we're working with all these pack prims in Houdini, it doesn't know what shaders are assigned to what inside of the pack primitive, so we have to export all the shaders. So when that gets to be a large amount of shaders, it takes a very long time, uses batch license time just for compiling shaders, which is unnecessary. So we try to be as efficient as possible, and we pre-compile those just using the saved cache code option on the OTL, which will lock that particular shader, and all the VEX code is cached. Yeah. So that's basically our workflow. Thank you. Yeah, if you have any questions. I know it's a lot to take in all at once, but yeah.
I was just wondering if you needed to write custom tools on the Maya side to export the transforms to alembic so that they would come into Houdini correctly?
Yes, we have some tools that go through there and will generate that point cloud for us. So it basically collapses all the transformation matrices and returns that to us. But on the Maya side, just for instance objects, there's, and the exporting part, we have some proprietary tools for that too. Yeah, thanks. Mm-hmm. I have a nice reel. Yeah, sure. But I do not have the audio plugged in right now. Sorry. Thank you. other questions, anyone? Cool. All right. Well, thanks, guys.